Alright, so our first colligative property is vapor pressure lowering. So when we make a solution by mixing a solute with a solvent, we lower the overall vapor pressure compared to solvent alone. So we're going to look at why that is. So let's say we have a 10% solution. So that means our solute would be 10%, our solvent would be the 90%. So if we look at this picture, the dark circles represent the solute molecules, the white circles represent the solvent molecules. So remember when we talked about vapor pressure before, we talked about molecules that could vaporize being on the surface. So only these surface molecules can vaporize and turn into gas molecules. When we have a solution that contains solute molecules as well, the solute molecules prevent solvent molecules from vaporizing because they're taking up space. So in this case, all of the white circles can vaporize because they're part of the solvent. The dark circle cannot vaporize because it's a solute molecule. Since it's taking up a spot from a solvent molecule, it prevents that molecule from vaporizing, thus lowering the amount of vapor pressure available. And when we look at how this works, we see an uneven distribution between vaporization and condensation. So all of our solvent molecules can vaporize, solute molecules cannot, but every solvent molecule that did turn into a gas molecule can then recondense back. Right, so overall this leads to less vapor pressure because we have less molecules that can vaporize, but everything that can vaporize can recondense. Alright, so that means that we have a vapor pressure lowering based on the concentration of our solution. The more solute molecules that we have, the lower the vapor pressure becomes. So we have a very simple equation for Raoult's law of vapor pressure. It says that the vapor pressure above the solution is equal to the mole fraction of the solvent. So in our example, we had a 10% solute solution, which would be 90% solvent. So this is our mole fraction of 0.9 times the pressure of the solvent by itself. So really when you look at this, the vapor pressure is lowering based on the mole fraction, which is our units of concentration. So more simply written, vapor pressure is equal to mole fraction, giant X, times pure solvent pressure. So where does mole fraction come from? You may remember mole fraction from Dalton's laws of partial pressure calculations, and it's the same idea here. Mole fraction is just the moles from our solvent divided by total moles, which is going to be solvent plus our solute. Alright, so it's a mole ratio. So if we look at what's happening based on our phase diagram, vapor pressure is going to be lowering when we make a solution. We have less vapor coming from the surface molecules. Condensation remains the same, so overall less vapor is present. The higher the concentration, the less vapor is going to be there. So if we look at how this affects our boiling point equilibrium line, we can see a shifting between the solvent by itself, so given in the pink line, here's our boiling line, equilibrium line for solvent alone. In the presence of the solution, it shifts to the right because it takes more energy to get the vapor back to where it was. All right, so we're going to have a higher temperatures required to get enough vapor because we have less vapor there. This is then going to cause a shift in both boiling point and freezing point, which we'll look at later. So for now, we're going to look at the math associated with the vapor pressure. So what is the vapor pressure of the solution when 65 grams of glycerin is added to 300 mils of water at 40 degrees? So we have our very simple equation. Vapor pressure is equal to mole fraction of solvent times the pure pressure. Now down here we're given a few constants, including the pure pressure. So vapor pressure of pure water is here, so we need this for our equation. And then we also have the density of water, because we're going to have to do a little bit of conversion to get our mole fraction. Alright, so let's see what we have. Since we already have our pure pressure, we need to concentrate on getting our mole fraction of solvent. So mole fraction of solvent is going to be moles of our solvent over total moles, which is moles of solvent plus moles of solute. Alright, so our solvent is going to be the water, and we had 300 mils of water, so let's find that first. Moles of solvent. We're going to turn our 300 mils into moles. So this is where our density comes in. We're going to use density to turn milliliters into grams, and then we can turn grams into moles. So I'm going to multiply my milliliters times my density, and this will cancel out my milliliters, and now I have grams. Then I'm going to use my molar mass to turn grams into moles. Alright, so 300 mils times 0.992 for our density divided by our molar mass. So 16.53 moles of the solvent. Alright, so the next thing we're going to need is moles of solute to do the bottom part. Our solute is going to be the 65 grams of glycerin, and we're going to use this formula to get the molar mass. So we have 65 grams. We're going to turn this into moles with our molar mass. So let's see. Oops. We have 3 oxygens at 16 each, plus 8 for our hydrogens, plus 3 times 12 for our carbons. Oh, that is not at all right. Let's try again. 16 times 3 plus 8 plus 3 times 12. Alright, 92 for our molar mass. So we're going to divide by our molar mass, and we have 65 divided by 92, 0.7065. So this will be our moles of solute. Alright, so now we can plug both these values in to find our mole fraction. Alright, so moles of solvent are going to go on top. That's our 16.53. On the bottom, we're going to add 16.53 plus our 0.7065. Alright, to get our mole fraction. So 16.53 divided by 16.53 plus 0.7065. Alright, 0.95 for our mole fraction. Alright, so now we're going to take that value and plug it in. So we're looking for our vapor pressure. We now have our mole fraction for our solvent, and we're going to multiply it by the 54.74 torr, which was the number we had up here for our pure pressure of water. Alright, so when we multiply, we get 52.5 torr. So same units we had here. So this is our new vapor pressure. It's lowered slightly from just having the water by itself because we've added a solute. Alright, we can also use electrolyte solutions for the same idea. Remember, with the electrolytes we have to incorporate an I value. Now, unlike the other examples that you're going to see with boiling point or freezing point or osmotic pressure, incorporation of the I here involves a lot more changes to the equation. So we're going to take our very simple vapor pressure equation, and it gets a little bit more complicated with an electrolyte solution. For the electrolyte solution, we're going to look at change in vapor pressure instead of just vapor pressure equals to mole fraction of solute, right? Solute this time instead of solvent, times our pure pressure times I. So we've incorporated a few different things this time. We have change in pressure instead of just vapor pressure, and we have mole fraction of solute instead of solvent, and we're incorporating the I value. Alright, so the most changes occurred in this equation. Alright, let's plug in what we know in order to find vapor pressure then. We have 75 grams of our sodium chloride, which means our I value is going to be 2.25 kilograms of water at 22 degrees Celsius. And then we're given our pure pressure, 19.8 millimeters of mercury for the water by itself. Alright, so let's plug in what we have. We're solving for our change in pressure. We know our I value, we know our pure pressure. So what we need to find is our mole fraction of solute. Alright, so let's see. In this case, we want our sodium chloride, our solute, to go on the top, and we need to convert it to moles. So we have 75 grams. We're going to divide by molar mass in order to get moles on the top. Alright, so this will be our moles for our sodium chloride. On the bottom, we're going to have the same ratio in order to get the moles of solute, and we have to add the moles of solvent. Now in this case we have 2.25 kilograms. I'm going to turn that into grams, so moving the decimal place 3 places, and then dividing by the molar mass of water to give me the moles of water. Alright, so all of this lets us calculate our mole fraction. Then our pure pressure, 19.8 times our I value of 2. Alright, so now let's do our math to get our mole fraction of solute. So 75 divided by 58.5. This is my moles of my sodium chloride, which goes on the top. We're going to divide by that second answer, divide by that same thing, plus our moles of water. Alright, 0.01015 is our mole fraction, times our 19.8 times 2. Alright, so times 19.8 times 2. So 0.4. So our change in vapor pressure is 0.4, and this would be millimeters of mercury. Now notice this is change, alright, our triangle means change, and not the actual vapor pressure. So if we want to find the vapor pressure, we're going to take the original pure pressure minus our change that we calculated. So this gives us 19.4 millimeters of mercury for our new vapor pressure. And we always subtract because remember vapor pressure decreases. So we're going to subtract our change from whatever the pure pressure was. So if we have an electrolyte solution, we have to do our equation a little bit differently. We find mole fraction of solute, we incorporate the I, and we find change in vapor pressure.